them. Magnets. Yeah. Hi, how you doing? Um, so, yeah. So I prepared. Yeah, what did I prepare? I prepared some slides with some electrical and physical details, as of like physics details, and yeah, I would start with like with that, and afterwards we will look at MPF, how it works in MPF. So, welcome and let's go into this. So this is our agenda here. Let me get it up quickly. So we will first go into like theory of operations of a magnet. I'm not sure if everybody is like familiar with electromagnets. If not, afterwards you will understand how they work, at least basically. Then we go into the nasty physics details and why you think that like a magnet like this, it has two wires, there's nothing much to it. And physically, it's like actually quite complicated, and there are even stuff which we cannot really calculate. So it's like there's stuff which you need to use numerical math to calculate how it actually behaves. So it's like a little bit weird. I didn't expect that when I visited university, but that's what they told me. And Wikipedia confirmed, so it must be true. And afterwards we will go like into the electronic details, especially how you use like magnets in pinball and why certain stuff is like done in certain ways. And we will talk about like applications, but you probably have seen it in pinball. There are a few, and then like a small checklist. So what to do and what maybe not to do with the magnet. So let's go into it. So first, theory of operations. So we are talking about electromagnets, right? This one, like that's. So what is this? That's a coil. Basically, it's just a few windings around this plastic shaft, and then there's the core. That's this metal piece here. So that's like, I guess it's actually steel. So it's just a magnetic, and not a magnetic. It's a ferromagnetic core. So it has to be some material which actually is basically it's not magnetic, but it can be like attracted by a magnet. So ferromagnetic, that's what it's called. And like this coil goes around like the core. And this also works without the core, but it's a lot weaker. So it's like, I don't know. You can calculate it. It's not that complicated to calculate the difference, but that makes it like really a lot stronger. That's why you want this in. It has like some more details to it, and we will come to that too. Usually, like you got multiple windings here, so like a few hundred around, and yeah, obviously your ball is metal, right? So a magnet can actually attract your ball. That's why you're doing that. So how much stronger is it if the core pokes through the playfield? We will actually have this in the next. I got like actually the formula on the next slide. But I guess you get the idea, right? So you got this like those windings around the core, and the magnetic field goes in here and out here, and like the length here doesn't really matter. What matters is the amount of windings. So it's like, I mean, there's probably some difference, but it really doesn't matter how thick the coil is. Doesn't really matter. It also doesn't matter how long the core is, at least not really. What matters is like they call it the air gap. So the gap between the ball and and your metal piece of metal. And then I guess Not sure. I would like treat like wood similar to like air, but yeah, so we will come to that next. But that's basically, I guess that's clear, right? And the field is basically going around here. And it's closed. You had like magnetic north and south, but because like the ball is not a magnet itself, it doesn't matter where north and south is, so it doesn't really matter. So now like the physics part, and I reduce it to the minimum stuff. So first you have to understand that the field, the magnetic field, is proportional to current multiplied by the number of windings. So you got more windings, that means the field will be stronger. Very simple, right? Unfortunately, also like if you got more windings, you will get more resistance. So like the overall resistance of this coil will increase. And for that reason, there's like some optimum around like a few hundred windings, and you cannot go with like 10,000 and it will get stronger, because then you will just need like thicker wires. Otherwise, like you won't get enough current anymore. So that's what you need to understand. That's like how strong a magnet gets if you turn it on permanently. Unfortunately, we're not doing that in pinball. So we're not turning this on permanently. Because we got very high voltages and those would simply burn. And now the question is, why don't they burn if you just turn them on? And the reason for that is like it's called the permeability of the core, so like of this material here, and that limits how fast the current can grow. So it's a little bit complicated, and that's the part where you need like numerical mathematics, because it's not like that you can accurately describe it, but more or less it's like if you got a certain magnetic field that limits how strong the current can be, or how high the current can be, and it can only increase a little bit. So like the magnetic field cannot go from 0 to 1000%. That's impossible. It can only grow over time. And for that reason, you can like turn it on for a certain time, and that won't cause issues, and it will build up the field over time. Initially, the current is low, and it will increase. So those magnets got like a really low resistance of, I don't know. I got like a multimeter, so we can check later how high this actually is, but I would expect it around like 2-digit ohms, so maybe even single digits, I don't know, but really low resistance, so that current would become really high at 48 volts. And that's also like the reason, because that's why you do not want to enable them permanently, because actually this will cause a lot of heat, and you probably have seen it in older machines where it's actually like where it's like the playfield is black from below, or it actually started burning, and that's not something you want. So to your question, like what's the difference between like this magnet, which is I mean, you partially embed it into the playfield. I mean, you can see this, right? So it goes like, I don't know, 6 millimeters into the playfield, but then basically there's like a few millimeters of wood left on top of it. And then this one, which actually goes through. And so like the force, that's what you're interested in. The force is actually calculated by that formula there. That's the magnetic field to the power of 2. Well, it's nice. So it goes up square. So to the power of 2. So that's basically not exponential, but yeah, it's quadratic. Yeah, and then multiplied by the diameter of the core. So like, or the area of the core actually. So you got a bigger core. So like, yeah, right. So you got a bigger core here. Magnet will be stronger. Also like, but the winding will be longer. So it's again a trade-off. And then the force will be like against to the power of 2. So double the distance between the two will halve the force every time. So now you can think about it, like 6 millimeters more or less. If you if the ball is like 2 centimeters from the core, that's not so much, right? It's if you like, I mean, you usually do not have issues when the ball is like in the center here. You got issues if it's farther away, right? And from there, I would say like 6 millimeters isn't that much, because like it's not like the power to the top, but it's to the side, and then you got like even the diagonal force there. So I would guess it's not that much. This is mostly done for wear reasons. So because this will actually really destroy your playfield on top if you grab the ball, yeah, or the clear will break off at some point, and the color will turn bad. I mean, we've seen it. And I mean, this also happens with those magnets, right? Because the core is relatively small. I know those newer Sterns, they got like larger cores, right? And I guess that's mostly to protect the playfield as for increasing the power. So yeah, those two types of magnets are like I would say the most common ones. So those are well available commercially, and they are inexpensive, just a few bucks. Yeah, so those are nice magnets. Hope that answers the question at least partially. So if you want to make it stronger, put in like more more power, and that will make it stronger. And like the problem is like the distance is actually to the power of 2. So now we got physics, we got like the theory of operations, and now we're just missing like the electronic details. And yeah, as I mentioned before, like we got like really high voltages. So like normally if you got a magnet which is like permanent, you would power it with like, I don't know, 6 volts or something. But in pinball, we want like this magnetic field to be there really, really quick. And as like the current cannot jump, it's like we need like really high voltage to energize, like to activate the magnetic field. And for that reason, we are running like really high voltages. That's the same reason for all the other coils. It's technically, it's not much of a difference between those coils with this core between any other coil which pushes out a ball or something. So those are really simple or really similar electronically, except that that this is basically mounted in like permanent, right? So, but in general, like the theory is very, very similar, and it doesn't matter which direction this coil is here. No difference whatsoever. Also, like you can swap the direction of the current, doesn't matter. So what we do in pinball is we run like pulses, like what we basically do everywhere, right? So we run like a short initial pulse of like 20, 30 milliseconds, something, and then we PWM it. So we turn it off on, off on, off on. And that's actually the same for all the coils. And that will basically then maintain a certain level of magnetic field. So like it's also the same for the current cannot raise like instantly. It can also not fall instantly. So like the magnetic field will stay here. So, and especially if you got a core, that causes like the magnetic field to raise and decrease and increase and decrease slower. And for that reason, we keep the core and not energized, but we keep like the magnetic field active inside the core. And that's with PWN, we just add a little bit energy constantly. So we keep it at a certain energy level. That's in a layman's terms, that's what happens. And for that reason, we usually got a FET or like a driver on your driver board, and that turns the coil or the current on and off, on and off, on and off, like at 1 kilohertz or something. Unfortunately, when you turn off a coil, the magnetic field is still there, and it then will act like a dynamo, so it will actually induce a voltage on this connector. And the voltage is actually inverse, so you connect it to 48 volts, and then you remove it. And now I take your guess, what do you think, how high is like the voltage if you just disconnect the coil? And like let's say 10 milliseconds after you disconnect the coil. So what do you think? How high is like the voltage at this connector at that point? Is it like, I don't know, is it 1 volt, 10, 100, 50, 1000? What do you think? So you would guess, yeah, you would guess 48 volts. So that's what you had before. But as like the the change in current is really, really steep at this point, and it's basically inverted, you get a really high voltage. So if you know like electric fences, like on where you got cows and or something, those actually work by, or not anymore, but earlier they worked by using like a low voltage, adding it to a coil, and then disconnecting one of the leads, and then putting that coil voltage on the electric fence. And that's exactly how they used to work previously. Sometimes they also still work this way, and you get actually a few thousand volts usually. And so it actually really hurts if you touch it. It's not dangerous, but it hurts. And that's also what happens here. And you got like inverted voltage. And now, like your typical FETs on your driver, they don't like inverted voltages. And for that reason, you need like a free flow diode. It's actually a diode which is inverted. So it will flow like the negative voltage here. And that will prevent this from flowing back the wires, causing like high frequency emissions, which is like if you want to sell the machine, that would like prevent you from getting any certifications. But it will also like damage your FET on your driver board and cause like a lot of noise on your ground line. It may like it may cause problems with serial LEDs, for example, but also like even for microcontrollers, this can cause problems. And that's usually worse for magnets because you build up a lot more magnetic field in magnets than you would do in any other coil. So that's really important, and that should be a takeaway from today. Add a free flow diode to your magnets. Otherwise, they will work like 10 times, and afterwards your driver will be stuck on. It happened to too many people already. Like in our forum, we got a report like every few months we see somebody getting a stuck on driver on magnets. So do that. Then as I told you earlier, they may get hot. So what those magnets often have, and this one also has it, it's hard to see. I'll probably show you like on the other camera here. So like this is basically just the coil, just the coil. And you see that here it's actually, there's like something which is not round. And if you look really close from below, you can you might guess that there's something, and that's actually a resistor, and it's basically for thermal protection. So that's a resistor which has a low resistance by default, so it's actually around zero ohms. But when it becomes hot, the resistance will increase. so that actually the coil will basically stop working until it cools down. And that's basically to protect you from burning up your machine accidentally. So that's really, really important to have this. But that's often on those coils already. Sometimes they break and you can remove them, but then you should just be a little bit more careful because they are there for a reason. Yeah, that's basically the electronic stuff, right? Pulse it initially, then PWM it. PWM it. And yeah, so that's the other one here. And now we can just, for once, we can check. You can probably see this, right? If we can check like the resistance here, and we can see how high the resistance is. Find out how it is. So there it is. Let's see if it works. Yeah, 0. And now we can like check this magnet here. See, it's like 4.8 ohms. So that's not very much. So if you look at 48 volts at 4.8 ohms, that would be 10 amps. And most power supply units, that's the limit what they can do, right? So this would like run at 10 amps, and that would like then burn how much is it? 480 watts of power. And you don't guess that this coil can cool 480 watts of power. That's simply not happening. It will burn quickly. Let's check the other one, but it should be similar. Yeah, it's actually the same. So maybe it's actually the same coil. I'm not sure. We bought those. This is like 20. You can probably look up how many windings they got, and yeah, ND, that's usually like no diode. So that's this coil doesn't have a diode, but they both got this one also has like the thermal resistor here. A bit hard to see on camera, but yeah, here it is. So yeah, they're similar. We can probably exchange them. And then yeah, this one is basically the other core, which you can screw in and out a little bit here, right? And then you can fix it here. So that's the two magnets I got. And the other one is just this core, and that doesn't go through at all. So that's the stuff already. Now we go to like to our applications. I guess that's not so surprising for you guys. So what can a magnet do? The first, it can obviously grab a ball, and for that it needs like some trigger, something, usually like an opto, which is near the magnet, often like in the direction where the ball is like coming from. So a few centimeters before the magnet, you got an opto, and then you grab the ball. That's like an application which works really, really well. If you put like the opto behind the magnet, then you often would not be able to grab the ball, because then the force is in the opposite direction, and you would have to put in a lot of force. So sometimes you also got an opto on both sides between opto, magnet, opto, so that you can like grab balls from both directions. That's relatively common. And then what you can do with a magnet is like you can fling a ball. So basically the magnet grabs the ball. I wish I had a ball now, but I don't. So it grabs the ball here on the playfield, and then it releases the ball. And after like a few milliseconds, it will then pulse the coil again. So the ball will go up. So it will get energy and just roll, basically passes the magnet, so over the magnet. And the pulse has to be just short enough so that the coil is already like off when the ball reaches the core. So it has to be like it gets energized when it moves towards the core, and then it just keeps its momentum. So that's a typical application. Sometimes you put it like, I don't know, below some ramp, and then the magnet can move it up the ramp, or it can pull it out of a drain, or even sometimes you got those magnets which are between the flipper fingers, and it can grab the ball and then fling it up into the playfield, into the game again, as kind of ball safe. And then obviously, like, it can grab the ball and drop it down, or release it. That's simple. But what it also can do is, like, it can accelerate the ball. So if you got the same setup as before, you got an opto, then you got the magnet, and maybe an opto afterwards. Then when it reaches that opto, you can just pulse the magnet, and it will accelerate the ball in the direction it is currently moving. And that's something, I don't know, for example, this it's like Star Wars, right? The Star Wars flipper from Stern, where it has this large heavy trails, where the ball accelerates more and more. That's done via a magnet to accelerate it. And I think there are a few like pinballs where it's done like in the lower play field. I'm not sure which one it is, but some of you guys got like a pinball where you accelerate balls like in the lower playfield, in a kind of orbit in the lower playfield. But that's something which also works. So I guess that's the four main use cases for like magnets. You can also like do stuff like where you got a rod which has a magnet, and then the ball is rolling underneath the rod. Those applications also work, but they are tricky, because if you got like some metal rod, you can connect it to a magnet, but at some point they will usually turn magnetic. So if you turn on the magnet often enough, at some point it will turn magnetic. So you need some special stuff to demagnetize it. So either like a magnet, which is the second one, which is connected, basically inverted, or you need something to energize your magnet, basically also like with inverted current. And so that's sometimes tricky. Some machines do it, but you see that like there are sometimes two magnets connected to it, or you have to make it that the ball has enough energy at the end so that it jumps off, or something like because if it stays there, if it's stuck, that's not fun anymore. So we tried this in our machine, for example, and that didn't work really well for us. But like, yeah, you can do cool stuff. Like you can also you catch up a ball and move it with some crane and then drop it again. In mechs, there's a lot is possible, but like those four applications are what you usually can do with this kind of magnet, right? What you use them for. And now I got like more checklists of your do's and don'ts. The first, fuse your magnet. So if something goes bad, they draw as we just mentioned, it would draw like 10 amps of power. That would really that causes a lot of heat, and that will burn. So add a fuse, and that will prevent the really bad stuff. Then use those thermal fuses, so those resistors, which are here or on here. Use that. You most have it, but just make sure you get one with a thermal fuse. It will just turn it off when it gets too hot. And ideally just do not run it at such high power that it gets hot at all. So test this a little bit, and when you turn them on, just check if it's getting too hot, then reduce the power. And add a pre-flow diode, otherwise your drivers will totally burn. And even I guess you do not want to prevent your neighbors from using a radio, because that will emit a lot of like HF transmissions. So yeah, adding free flow diode. And yeah, use like a pulse and PWM. Never ever just enable magnets. That's bad. Just use like pulse and PWM. That's already it for like my theoretical part. Looks like I talked for half an hour, so it's not even short. But that's it. And now I will show you like how I would like configure magnets, or like how you configure magnets in MPF. So this is my small IDE again, and it's gone again. So first we basically need a switch, and what I did here is like I defined a switch which is just called switch orbit left. So to just pretend it's like I got that magnet in my orbit, and I got like some opto in my orbit as well. If it's an opto, you typically got like type normally closed, because they are often inverted. So that's what you typically would have here. Has some number, depends on your platform. And then we got a coil. So yeah, as I told you probably 10 times now, that's coil. And this connects to your normal driver board. And this also has a number. And then you got like some default pulse milliseconds. That's basically the initial pulse it will give it. And then you also want like default, come on, default hold power. And that's basically a float number between 0 and 1. So 0% to 100%. For most platforms, it's like, it's like you can have either like 12%, 25%, so they got like 8 or 10, sometimes 32 different strength you can do like in PWM. But I would say like typically you want like something like 0.2 or 0.3, but something around that, and not like 0.5 or 0.8. It will be like just too much. So just keep that low and just check that it's still strong enough. So most of it will come like from the initial pulse, not from the hold power. That's just to keep the ball from falling off. So you can often keep that really, really low. Only like if you want to prevent another ball from kicking the ball off, then you would have to increase like the hold power. So that's what you put on your magnet, on your coil. And then we define the magnet itself, like in the magnet section. As you might guess from the name, we got like grab switch, this has orbit left, and we got the magnet coil, and that's like this magnet we just, this coil, this magnet coil we just defined. Now that's done. And so what we can do now is we can have like enable and disable events. So often you would say like in certain modes you enable this. Maybe if you saw my last stream, you would probably have some state machine, and in certain states when it wants the magnet to be enabled, it will then enable the magnet. And what that does in a magnet is, so like let's say like enable magnet would be our enable event, and we got probably also disable magnet. And now once I post like enable magnet, it will add like an event handler for this switch here. And once the switch becomes active, it will pulse the coil or enable pulse and then enable the coil to grab the ball. That's what it would do. And after it grabbed the ball, it will basically post an event that just means that it fired and it enabled now. doesn't mean that it necessarily got the ball. So depending on your application, you might also want like another opto on top of your magnet to see if you actually got the ball or not, because the magnet actually does not know. So that's just something also to think about. So if you just want to like grab a ball and drop it, and it doesn't really matter if you succeeded or not, then you do not need it, but sometimes that's also useful. And then now the ball is then grabbed by the magnet. So it grabbed the ball and it's active. Now we just produce heat and the ball won't move. So what you can do now is like, you got a few events. One is like release ball events. So release ball, maybe. If you like, for some reason you want to release the ball, post that event, the magnet will release the ball. So simple. And then you got like those fling stuff. That's basically, you can have like a fling ball event, and then you can say fling ball. It will then drop the ball, so release the magnet, wait a few milliseconds, and then pulse the magnet. So it will basically drag the ball up, and the ball keeps the momentum and moves up. And then, as you probably see on autocomplete, there's a fling drop time. So for example, I would say like we drop the ball for like 100 milliseconds. Maybe, I don't know what you need, something 100, 200, 300, something. And then, you got like the re-grab time, and that's basically for how long it would then pulse the magnet. Let's say, I don't know, 50 milliseconds. That's also the default. But something around that. So that's basically the amount of energy you put in. And so you have to play with those values depending on the playfield angle, your magnet, and a few parameters. So like if you just drop it more, you can put in more energy afterwards, right? And you can put in longer regrab times. But it may also happen that it drops so far that the magnet is too weak to pull it up afterwards. So play with it a little bit. And now with the default is here 250. So that's the ballpark what you want to use here. So do we have something else? That's basically already what it is. So that's what the basic magnet device does in MPF. And everything around that is basically your logic. I would personally just recommend state machine, which decides what to do when, depending on like a second opto, for example. So like if you just want to accelerate a ball, that's also something which should be mentioned. You do not even need like a magnet at all. So in that case, you would probably use like something like coil player and just say like, let's just say we got like a switch which is S orbit accelerate. Oh no, let's say we got like this opto and then the magnet afterwards, and the ball comes from here, goes to the opto, and the magnet is after the opto. So we could say this coil player is like on S orbit left active. So when this switch becomes active, we would just say like this coil should be pulsed. And that would basically do this acceleration stuff. You could even do like define an auto fire coil, so like it's like this, so like a pop bumper, where you delegate like this pulse to the hardware. But that really depends on how your timing, how firm your timings are. Like the hardware will be lot more, maybe a lot more accurate, but that also has like some limitations. Sometimes you want like a delay after the switch. That's not something all hardware platforms can do. But if you want to do something like this, let us know in the forum. We can help. So there are ways to just to write like hardware rules in most platforms. But so far, I'm not sure how people are doing it. So I guess some will actually write like Python code to write the hardware rule on their own. But that would be something I would recommend to ask in our forum, because there are people which know. But that's not what a lot of machines do with like accelerating boards all the time. So with like grabbing, releasing balls, that's what you would do with the magnet usually. And yeah, that's for like accelerating it. Yeah, that's already what I got basically. And that's really like, it's really simple to control magnets in MPF, define them, and yeah, you can then base your logic on this magnet device. Yeah. So currently MPF does not use like hardware rules for grabbing the initial ball. The reason for that is like a little bit that not all platforms support enabling a coil based on just one switch hit without that the switch is kept active. So, but some platforms could do this like in hardware. So if you need like really accurate grabs, let us know. We can also help with that. We would then add this to the magnet device. But for most applications, just like 10 milliseconds just do not matter, because the ball will not travel that far within 10 milliseconds. So that still works fine in most cases. Yeah, so that's already what I wanted to show. So if you got any questions, I'm happy to answer those. And otherwise, yeah, we can also look at like my my two magnets again, and yeah, whatever you want. It's all possible. So, yeah. So that's the two magnets and MPF controlling magnets. So yeah, and there are no more questions. Okay. Any considerations about keeping stuff away from magnets, lights, switches, other coils? I guess let's start with the easy stuff. Switches shouldn't be like an issue. I mean, if the magnet like mechanically touches the switch, that's bad. I guess it would just keep the switch down. But unless there's like a few millimeter space with a switch, I don't think you will have any issues. Same for coils. I mean, they just induce magnetic fields themselves, so it's coils and coils. They like each other. For lights, it depends a little bit. For like normal LEDs and bulbs, that shouldn't be an issue. For serial LEDs, I mean, just keep them. I guess it's less a problem for the magnet itself here, because there the field is really channeled out here. So it's really, field is the strongest here. Not here, it's the weakest on the side. It's the strongest here. So that, I mean, you do not want to put it on top probably, but if you put a serial LED next to it, that shouldn't be much an issue. But I would just basically look after the wiring. So most of the interference from this coil will be between those two wires. So they are basically, this acts like an antenna. So between the two wires, right? So keep those close together. Do not just basically run ground here and high voltage here. Just keep them together like this. And I would keep serial LEDs away from the power wiring of any coil, not just magnets, but it's more important for any other magnets. So keep this together. That will keep you basically all those interferences and high frequency emissions away. And that's also what I would keep my lights away. So my serial lights, I would keep my serial lights away from that. Also something which is like always important is run separate grounds from your power distribution to your lights and to your coils. So just run one power for 5 volts for your lights or 12 volts and one ground for high voltage. I mean, connect them at your power supply, but at the power supply outside the playfield, not below the playfield, because otherwise you will have, if you turn off the coil, ground will stay connected to the other side, and that will basically induce like this inverse voltage to the ground line, and that will cause interferences in your serial LEDs, and that they don't like that. I mean, even your logic power, like the power for your CPU boards, like for your node boards, that will also not like any interferences in ground. And so just keep those separate a little bit, right? So it's one high voltage ground, and light power and light ground. Connect the grounds outside the playfield, but not below the playfield. That's important. If I'm daisy chaining the ground, just keep both wires away from everything else. Yes. And if you look like at this stern, what they do is they got like some wire harness, and it goes like this. So here you got those two wires coming, and now ground will go in here together with another wire, and it will basically go out at almost the same place. So they also do not just have ground this way, connected this way, and power another way. So keep those two in parallel. Even if you daisy chain, keep ground and your power feed in parallel. That's always a good idea. And even, I mean, that's not so important in pinball, but basically to prevent any like weird interferences, it's in high voltage and on high frequency stuff, it's even important to keep the length of your wires the same. So ground and the power wire should have the same length. That's also important. So that's why just route them next to each other all the time, that they're the same length. If they shouldn't be very different lengths. That's I mean, it's not a guarantee for disaster, but it often leads to issues later. So keep those the same, keep this together, and you won't have issues with all this interference stuff, especially with high voltage or high current. It's not high voltage, it's high current. So where those, like all this magnetic stuff happens if you got high currents. Basically, I mean a wire that's just the same as in your magnet here. It's just only one wire, and this is just the 10 or 100 spins around, or windings, or 100. So it will create an magnetic field, and basically, yeah, you're creating an electric magnet if you just put two wires like this. That's basically a magnet. And it's still a magnet, but now the field is just between those two wires, and outside those two it will be not nothing, but they will mostly neutralize each other. That's that's all what happens here. And basically you're transmitting at 1 kilohertz, and then like there's the multiplies of 1 kilohertz. You're transmitting some signal there from your machine. You want to keep that low. Now I talked a lot of that, but it's common to have issues there. Yeah, so in my experience, like, I mean, you can even run serial LEDs next to it. It won't cause any issues. So in my machine, I run like, I think we got 24 chains of serial LEDs or something with 500 serial LEDs. And we do not have any issues even next to coils or so. We had a lot of, we thought we would have a lot of problems, but all those fears turned out to be not necessary at the end, as long as you just power your LEDs. So for serial LEDs, again, another detour. For serial LEDs, it's important that they got enough supply voltage. So if that drops too much, then like the white point shifts and also they become unreliable. And that's also already below like 4.5 volts. So it's not like they even work down to like 3 something volts, but according to the specifications, it's 4.5 volts. That's what you want to have at least. And below that, they might become unstable because it's out of specification. And just measure that. Have a scope and or like a multimeter and check that the voltage is actually fine with your serial LEDs when they run at full brightness at the end of your chain. So that should be really still your 5 volts or 4.5 volts, and then you will be fine. But in general, don't worry too much. You will find out later. I mean, you will make so many mistakes in pinball, and rewiring is not the end of the world. You will probably do it a few times anyway. So, from bad to worse to okay, and then eventually to good. That's what I would say. That's what most homebrews go from to. Yeah. Anything else you want to know or want to talk about? Any remarks? Any wishes for the next stream? What you want to see? Or not? What? I want to do like something on fast. Like I don't know, maybe next week I will do something on the fast system. I got like a few boards laying around at home, but I do not have like a nano laying around at the moment. I need to get one, but it's deep inside the machine, so I need to unscrew it and connect some stuff. And yeah, problem is I need to do it, and I didn't do it yet. And then I need to build like some demonstration system for that. Also got like some new system coming up, which I teased a few times, but I'm still like writing the platform code for it, so it's not really working yet. Maybe we'll have Cobra pin soon. See when it will be here. And besides that, there's a lot of exciting software stuff to check out, and we'll probably have some more like streams on software. So yeah, guess that's it for today. Thanks for joining, everybody. It's a pleasure. Yeah, if you have any remarks, write me afterwards. We will probably see in one of the many chats. And hope to see you soon. Maybe on Saturday. I will like announce the topic probably on Friday. And until then, have a great day. Have a great remaining week, and see you soon, guys.